neuromorphic engineer in Adera, and I am going to present end-to-end application generation and deployment for neuromorphic microcontrollers. So there are sensors everywhere, right? And there are also lots of types of sensors, ranging from acoustic, temperature, acceleration, vision, you name it. Not only they are everywhere, but there are going to be way more in the future. So by 2030, billions of active sensors are going to be there, and they are going to be outputting data that we cannot process in the cloud. So the edge is not optional, it's inevitable. We identify that current normal microcontrollers mainly do tasks such as feature extraction or adjusting or calibrating a sensor, which they are not quite compute intensive, right? So like they lack some compute to be able to process all of this data, and that's where the chips that we're designing are going towards, to enhance this computing power whilst staying in this power range for the microcontrollers. That allows us to develop applications for many domains, such as consumer electronics, IoT and smart home, industrial applications, and wearables. We're going to focus a bit more on wearables in this talk, because we have a gesture recognition application that you can actually visit and play with in our booth. So let's keep going. Okay, so we have said that there are many sensors, and there are many types of sensors, right? That tells you that compute on the edge needs certain flexibility. That's why we have an heterogeneous architecture. That also, because we need to increase the power as we established already, while being power efficient. So, well, this is the heterogeneous architecture of Adera's chips. As you can see here, well, there is a CPU, a RISC V CPU, so that you can do general purpose tasks, also like some sort of common interfacing, and then we mainly have a tiny CNN accelerator, and then an SNN, or spiking neural network accelerator, which you can also call a neuron synapse array, which is our differentiation, and it's an accelerator for being able to process temporal data. Yes, so going a bit deeper on spiking neural networks that, as I have said, are so important to our chip. Normally, the typical flow or pipeline that you would use to use them is that you would get certain input data that is decimal or analog, and then you would encode this into binary events or spikes, which then would go through the network, and then after that you would maybe want to make a bit of sense out of it, maybe like translate it into probabilities or something like that, such that you can determine if the output is pattern A or pattern B, or there is certain feature in the sensor data. And we allow we can do this in our chip in many ways. As I said before, like we have quite an heterogeneous architecture, and which is quite flexible. So we could imagine that somehow you get certain data from the CPU, and then you could, for example, do this translation of the signal into spikes. You could do it in software, or in some dedicated hardware that is quite efficient that we have created for you, and then that will go through the SNN accelerator. And again, like if you want to create certain fancy or exotic type of decoding, which again is like making sense of what the spikes meant, you could do it in software, and also you could do it in hardware, and then this would trigger an action probably by the CPU, right? In order to be able to replicate this flow for any application that we target, we are using the Talamo software development kit. This software development kit allows you to train these really special networks by training them as in normal PyTorch or PyTorch-like in a PyTorch-like manner. It also integrates with standard software tools such as TensorBoard, just in case you want to know, like, okay, what the network is doing, is it going to fail, is it good enough? Then we are extending our software development kit with new tools, which would be the system compiler that will allow you to get this high-level PyTorch pipeline that you just trained, and it will generate a binary file that you can deploy in our chip, for example. We also extended the Talamo SDK capabilities with a system-on-chip simulator, so that you can take into account all the interactions between every component in our heterogeneous chip. I will exemplify this and the value of these tools with an example. So actually, I do not know how to play this, but I'm going to try. No. Okay, it doesn't matter. We have this application in our booth. Please come to check it out. In any case, the normal flow, as I was commenting before, is that you maybe have an IMU sensor. This normally entails having certain accelerometer data and certain gyroscope data, and you can translate this data into spikes using dedicated hardware. It's maybe not necessary to know specifically what these encoders do. Basically, the IF encoder will kind of translate the magnitude of the signal into spikes, and the temporal contrast encoder will translate the velocity of the hand gestures into spikes. We already have our spikes, then we can pass them through the SNN and then make sense of them and create an action. Well, this is how it looks like, by the way, if anybody is curious. So what does the system compiler, this thing that I was talking about before, do? Well, it kind of, from a high-level perspective, it's targeting the fact that there are certain barriers of entry for developers to use our chip, because you have to know more stuff because there are more components, right? So for the system compiler, we maybe have certain high-level pipeline or high-level primitives that you have trained, and in this case, like in our chip, you would have maybe certain connection of these software entities of your simulation with certain dedicated hardware that implements them quite efficiently. Otherwise, for example, since there are two temporal contrast encoders, and this hardware may be dedicated, then you could also run them in software. After the hardware assignment is done, then you basically can generate automatically certain low-level C code that then will be compiled and that you can deploy on our chip quite easily. You could deploy it on our chip, but what if you don't have our chip, or you are just prototyping something quickly, right? You need a system on chip simulator, not only an SNN simulator or a CNN simulator. No, you need the whole system to be simulated and functionally good. So we developed what we call the SOCSIM, which is basically it satisfies the necessity that our subsystem needs to be tightly coupled because of the time dependencies that the SNN have. So like the timing of the spikes is really important in SNNs. So this kind of addresses that problem and solves it functionally. It's a cycle approximate simulation of the whole system that ensures that if you want to deploy something on our chip and you don't have it, or you just want to verify something, then you can use this and it will have the same functionality. Well, how good these tools are, right? So we evaluated them using basically like a couple of KPIs that we consider important. One of them would be for the system compiler, which again is this software that translates your high-level pipelines into a binary file, basically. We saw that the static code size of this generated code by the system compiler is, in average, 37% higher than an app created by an expert, at the expense of it's automatical, like you do not need to really think about the implementation. Also, we see a small drawback in terms of power consumption because the system compiler is still not quite optimized, but the functionality is there, and we are working to optimize this even further. Regarding the SoC simulator, there is 100% accuracy, or if you want to call it that way. So there is a one-to-one match between what our chip would do and what the SoC simulator has predicted there would be. And we also want to highlight that it's quite fast for this kind of simulation, because theoretically it could be 1 to 5 times slower than running the whole thing on the chip, but in practically we saw that it's only 1.13 times slower. Well, the conclusions is that to be able to give access to developers to be able to use our chip efficiently, we need to and we are developing tools to make their life easier and to fully optimize for the characteristics of our chip. And we are going to continue developing these tools. Also, we just launched our new commercial chip. It's the first ultra low power neuromorphic chip, commercial neuromorphic chip in the market. It has already earned an award for the most innovative chip, and yeah, it's really efficient, and we are really looking forward for you to try it and engage it. Well, also I wanted to announce and recommend you to assist if you are more interested to join the workshop that there is going to be in 20 minutes, which will be held by my colleague Peter and Basile. in which they will discuss commercial, the commercial future and the ecosystem of neuromorphics in the years to come. So yeah, thank you very much for this.